The transaction abstraction is one of the most powerful tools in computing today, in modern computing, namely concurrent and distributed computing. The goal of this video is to give an intuition of the underlying semantics. To illustrate the semantics of this abstraction, I will consider two simple computations. The following one decrements the value of an integer x and then increments the value of an integer y. X and y are two integers. So let's call this t1. And the second computation is even simpler. It assigns to an integer variable z the sum of x and y. So assume initially that x equals 1, y equals 0, and z equals 0, and let's ask ourselves what would be the value of x, y, and z after executing t1 and t2. So if t1 executes before t2, then x will be 0, y will be 1, and z will be 1. Interestingly, we will get exactly the same result if t2 execute before t1. But what happens if t2 and t1 execute concurrently? So assume, for instance, that t1 and t2 are located on two different processors or two threads of the same processor, and they execute in parallel. So what might happen is that x minus 1 is computed first, which would lead that x to be 0, and exactly at this point z is computed, and here x is evaluated to 0 because it was just decremented, and then plus y, which is 0, leading z to be 0. And then later on, y will be incremented. So if t1 and t2 execute in parallel, we might have x equals 0, y equals 1, and z equals 0. This might be okay for certain applications, but assume x and y are the values of two bank accounts of a user, and what the user is doing is removing, let's say, 1 million from x and putting it into y, and z is supposed to compute the sum, to store the sum of the accounts, which is the total amount of money that the user has. So getting 0 will be a very bad surprise. So the transaction abstraction, the goal of the transaction abstraction is to prevent this situation from happening, this interference from happening. How is this achieved? To say that certain interferences should be avoided, the programmer has simply to do the following. By writing this, basically the programmer is saying that even if T1 and T2 are, let's say, located on two different processors, the situation where, let's call this T11, the first instruction, and T12, the situation where T11 executes, and then T2, and then T3, T12, is forbidden. So this interference is forbidden. Intuitively, we say that the transactions are atomic. So the power of the transaction abstraction is its simplicity. The programmer can surround any sequence of instructions with brackets saying that this has to be atomic. Sometimes we write atomic here, sometimes we write begin and end, etc. But bottom line, any sequence of instructions can be encapsulated inside a transaction with some specific construct. The sequence of instructions can be sophisticated. There can be control structures like if then else and all kinds of things. And this can be anywhere in the program. What is also important to understand is that by declaring this set of instructions, this sequence of instructions as atomic, the programmer doesn't need to be expert in concurrency. What is important here is that underlying this scheme, there is some transaction memory or monitor that prevent any interference. However, from the programmer's perspective, two things are important. One of them is transactions delay computations. Therefore, they need to be short. So intuitively, no matter which algorithm and hardware is used by the underlying transactional memory or monitor to avoid interferences, transactions delay computations. It slows them down. So they have to be as short as possible. The second thing that is important is that transactions might abort, and I will explain intuitively why. So assume very simple situation where we have two transactions, T1 and T2, and let's say T1 accesses variable x1, x2, etc. And then T2 accesses x prime 1, x prime 2, etc. And eventually both of them access xn. Most algorithms and schemes to implement the transaction abstraction, as I pointed out, called transaction memory or monitor, they will speculate in the sense that they will have T1 access x1, x2, etc., and T2 access x prime 1, x prime 2, etc., without doing anything special. But when they reach xn, they will have to do something to prevent interference. And what they typically do is abort either T1 or T2. So strictly speaking, a transaction is a computation that might abort or commit. It terminates in two states. If it aborts, its effects are invisible. So if this transaction here aborts, we don't see its effects. If it commits, it appears to execute at a single point in time. And the combination of these two properties constitute what is called atomicity. In other videos, I will explain what this atomicity means slightly more formally, and how it is implemented, namely what the transaction memory and monitor need to do to guarantee atomicity.